into Gauss's law. Last time we did a point charge, and this time we are going to do a charged plane or a charged sheet or charged plates. Basically, just imagine like a metallic sheet of paper, and we have charged that sheet of paper up. Let's begin. So, in order to show what we're really dealing with here, I'm going to do a quick little sketch of a charged plane. You'll notice here that I have the graph paper up, and it's just there to just help me, um, just draw a little bit better. All right, so here we have our charged piece of paper, and we'll just say this is a positively charged piece of paper, okay, or excuse me, a piece of metal paper. And we are going to now draw the field lines. So the field lines, because it's positive, the field lines will come out, come out, come out, come out. All right, so we have a positively charged plane, and we have the field lines, and all the field lines are coming out of this charged piece of paper. So what do we do next? Well, let's come up with a situation here. All right, let's come up with a purpose for all this. What we want to do is find the E field at a point X away from the sheet. And this point X can be anywhere. So I'm just gonna get my marker. Let's say, let's do green. Yeah, at point X right here. Okay, so some radial distance away. So if you're following along with your piece of paper, if we have a piece of paper here, we can say right here, that's our point X, okay, away from the sheet. What is the E field there? All right, so if you remember from the previous video, with the help of Gauss's law, not only can you determine the amount of charge that is enclosed in your Gaussian surface, you can also determine the E field that is enclosed from the Gaussian surface. They all go hand in hand. So let's go over how we can do that using the rules of the Gaussian surfaces. All right, so far, we've only covered the Gaussian sphere, okay? And if you want to use a Gaussian sphere now, well, we really can't, and I'll show you why. So I'm going to take that 3D image and just put it off on its side. Okay, so this is the charged piece of paper, and I'm going to do a quick sketch of the E fields coming out. Okay, so let's go over why we can't use the Gaussian sphere. I'm going to draw a Gaussian sphere right here. All right, so if I look at my Gaussian sphere here, there's a couple of rules that we must follow. One is the E field 90 degrees coming out of surface. Okay, so that's the first one. Okay, remember we were talking about all these tiny little windows, right, that the E field can come out of. So is the E field coming out at 90 degrees? 2, is the E field constant out of every window? 3, is the E field enclosed? Close, right? So those are the 3 requirements. So let's go over this one by one. Is the E field coming out at 90 degrees? And hopefully, right, you're saying, maybe at certain points, Mr. Lee, right? And the answer would be yes. So directly across, the one I'm drawing now, this E field, that would be the only one, or that one and this one, the 2 that I just drew. Let's use a highlighter to really show that these, only those are the 90-degree ones, okay? Because if you take a look at, let's do blue. Let's take a look at this E field, right? If we take a look at that E field, if I were to draw the window, so that's my window, right? My Gaussian surface window, and my E field coming out of it, look at that. It's not coming out at a 90-degree angle, right? And so the first one, not required. All right, this is E field constant. So now we got to think, okay, so we have our formula, KQ over R squared. I mean, we can see it, right? So the R here versus the R here versus, let's say, the R here, the R's are all over the place, right? The radial distance is all over the place, so the E field is not constant. The only requirement that this Gaussian surface really meets is the E field enclosed. Yeah, it's a sphere. We actually enclose it, but the other two requirements are not met. So how can we create a Gaussian surface? Well, here's the cool thing about Gaussian surfaces: it's whatever you want it to be. Okay, and like there's only so many Gaussian surfaces that you can really draw for certain scenarios, and it sort of makes sense once you go through them. So we use a Gaussian sphere to enclose a point charge, and the two kind of look the same, right? A charge looks like a sphere, and so the same idea will be used for this plate. So if we use a circle to enclose a point charge, why don't we use something that looks like a piece of paper, right? So if you're following along with your piece of paper, so this is my charged plate. What if we put a Gaussian surface like this, another piece of paper in front of it? So that would look a little bit like this. Let's use a different color. Yeah, let's use purple. All right, so this is my Gaussian surface right there. Okay, if that's my Gaussian surface, let's go over the requirements. Requirement number one, is the E field 90 degrees coming out of the surface? And I would say, yeah, that's good, right? Boom. Number two, is the E field constant? Oh, yeah, it is, right? Because if you take a look at it, the E field at this point and the E field at this point and the E field at this point, because it's all the same radial distance away from the plate, it's going to be constant. Okay, and number three, is the E field enclosed? And that is where this Gaussian surface falls apart. It's not enclosed. So back to the model. If we have a charged piece of paper and we have a Gaussian surface there, okay, what if we put another one here? And it will look something like this. Boop, 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 boop. Right, of course, it being the same distance away from the other side. Cool. Okay, so we are now enclosing the other side of the E fields. However, it's still not enclosed. And hopefully by now, you're trying to get my point. In order to enclose these Gaussian mirrors or these Gaussian windows, we just have to create a shape, right? So if you have a plane, if you have just a piece of paper or a plane, and you put another plane in front of it, you're not enclosing anything. So what you have to do is you have to, almost like connecting the dots here, right? I'm going to connect the surface from one point to the surface of the other. Okay, and when you do that, even though this is a 2D image, what you see is what we want. Okay, now this is enclosed, and so here, this is what we call our. This is a Gaussian box. Is it the official term? I don't think so. I don't think anyone calls it the Gaussian box except me. But kind of makes sense. It's a Gaussian box. Why did I put a question mark there? That should be an exclamation point. This is a Gaussian box. All right. So this is a 2D image. Let's show why this Gaussian box works with our requirements. Okay, so that's my charged piece of paper. I'm going to now draw my Gaussian box. I'll draw it in purple. All right, so okay, and then it goes out like this. Yeah, look at that. That's a nice Gaussian box. So this is on one side, and on the other side, we have the Gaussian box come out as well. This is my best artistic ability there. Oh, man. Yeah, that's a good Gaussian box. All right, so we have a imaginary Gaussian box that is enclosing a portion of this charged plate. Should we shade it in? There we go. Yeah, that's a nice Gaussian box. All right, so here we have a Gaussian box, and it is a Gaussian shape, and it has all the requirements met. Now, let's come up with a couple of terms. So I'm going to redraw my Gaussian box, maybe a little bit bigger. That was also a bit difficult to draw so small. So here's my Gaussian box. Oh yeah, look at that. That is a nice Gaussian box. Okay, so I'm going to call this side the front. I'm going to call this part the back. And I'm going to call that this, and the rest of the two sides, these are my sides. Okay, and the charge plate is enclosed within here, just like what you see here. And so we have the E field. Okay, we have the E field coming out here. The E field coming out on the front and the back. Over top, you do have and on the sides, you do have the E fields, but it's only the front and the back is where the E fields are actually coming out. And that's important because remember, for flux, time to remind ourselves of the formula, flux E dot D, E dot A. Okay, we want our E field to be coming out of the surface, right? Yeah, so in this case, our total net flux, we would get uh, flux of the front plus the flux of the back plus the flux of the side plus the flux of the side plus the flux of the side plus the flux of the side. All right, so we have, let's see, 1, 2, 3, 4, 5, 6. There we go. We have 6 faces of a box. But many of these sides of the box don't even have the E field coming out. So our flux is 0. And the parts where the fluxes are 0 are actually these 4 sides because the E field isn't coming out of those parts of the box. All right. So only the front of the box and the back of the box actually have the E fields coming out. So those are the only parts where we actually have flux. So this actually makes our math a lot simpler. If we were to rewrite our formula, we would say the flux is equal to the surface integral of E dot dA. And as a reminder, that dA is the shape that has that is a Gaussian surface shape. And we can say that this is equal to 2 of the fluxes. Okay, and the 2 of the fluxes is the flux of the front and the flux of the back. And because the E field is coming out of both of those sides, we can say that the E from the front is equal to E of the back, right? Because the E field is coming out of the front and it's coming out of the back. And I'm emphasizing the word out in this situation here. Okay, so we have 2 times the flux for our scenario, and we can finish the rest of the formula. We can say it is equal to Q enclosed over epsilon naught. And if you're wondering, where'd you get that, Mr. Lee? That is Gauss's law. Okay, so we're going to do a quick little sidetrack here. Okay, it's important to know that we are not looking at total Q because the total Q is the total sheet of paper. Okay, and it could be like infinitely big, and we don't want to look at the total sheet of paper. We only want to look at the Q enclosed. Okay, that's the important part. We're only looking at the Q enclosed, and that's a section or just a portion of that plate. And so in order to be able to describe just a portion of this plate, we have to create a ratio. And that ratio is called charge density. And charge density, in this case, it'll be for charge of a surface area, is represented by the Greek letter sigma. And it's just a ratio. It is equal to the total amount of charge divided by the total area of that sheet of paper. Okay, so that is our ratio. So if we take a section of this charge, and that will be just a portion of the area, we will get a portion of the charge, aka the Q enclosed. All right, so that's a big part of trying to figure all this out. So let's go back to the formula here. I'm going to go off on the side, kind of ran out of space there. We can say that, so let's do 2 phi is equal to Q enclosed over epsilon naught. And we know that phi, or flux, is equal to 2 E times our tiny little section of the area. Okay, so I'm going to represent that with a lowercase a. You could probably do that as a dA as well. Is equal to Q enclosed over epsilon naught. All right, and the reason why I wanted to show you this here is because through some algebraic manipulation, we can say that 2e is equal to Q enclosed over A times epsilon naught. Now, I'm going to highlight the portion that I want us to focus on, this portion here. That right there was the ratio that we just discussed. So we can rewrite it as 2e is equal to sigma divided by epsilon naught. And we can take this a little bit step further. E is equal to sigma divided by 2 epsilon naught as our final answer. If you go back to the very beginning, the question was, what is the E field at point X? Okay, so we extended out our Gaussian box to point X, and this is what we got. And yeah, so something I want you to notice here. Even though it's at point X, nowhere here, X isn't here. X isn't there. So what does this mean? It means that the E field is not distance dependent. The E field is not distance dependent. And there's a reason for this. Oh. I also want to extend out this formula. We can say that this is E Q over 2 epsilon naught A. So this is for a portion. Okay, so that's the E field for a portion, and this is the E field that we get for the whole. This is for the whole sheet, right? Because this is taking a look at the total charge. This is total Q, and this is total area. But here, this epsilon naught or this sigma, this is showing us. This is showing us. This is a portion. Okay. This is for the ratio. All right. So let's go over why it is not position dependent. So if you were to think about it, okay, let's say we were to shrink you down so that if we had this giant sheet of paper, right, and we were to put you like directly in front of that sheet of paper. And so what we're doing here is we're turning you into that Gaussian surface, right? We're turning you into that window. What you see heading towards you is the E fields, right? Because the E fields is like directly at you. So it's kind of like if you were to walk directly up to a brick wall, a giant brick wall, even like a building, okay? And you're like this close to the building, you would just see the brick wall. And if you were to take a couple of steps back, okay, you will still see that brick wall. And so you take a couple of steps back, you will still see that same brick wall. And so you seeing that brick wall is like you witnessing or you looking at the E field, okay? And the reason why this E field is not position dependent is because the Gaussian surface that we created was so small. Okay, and like ratio-wise, because the surface was small and we are a certain distance away, it seems just like a uniform field. Okay, the brick wall or the building itself doesn't change. So when does it matter? Well, in our analogy, we took a couple of steps back, right? But what if we were to go super far away? Right? Let's say out into space. So if you're looking at the brick wall and then you were to zoom out, right, we were to pull you back into space and you were to look at the same brick wall or that same building, it wouldn't look like a building anymore, right? The sheet of paper, in our analogy, wouldn't look like a sheet of paper. It would look like a point. And at that instance, we're not looking at a sheet of charged plane, but rather when our distance becomes so big and our Gaussian surface, because we're so far away, our Gaussian surface is basically just tiny, that's when the distance matters. But that's for another video. Anyways, this is the second video in our Gaussian surface series. I'll see you next time. Bye bye.